The ground shakes, not from an earthquake, from below. A steel door, 12 tons of it, swings open in the face of a mountain, and out of the rock, on rails, emerges a ballistic missile launcher. No launch pad, no gantry, no exposed infrastructure, just the mountain itself, opening like a wound, and a weapons system rolling into daylight that has never seen daylight before. This is not a bunker. Bunkers get destroyed. This is something different. A network of tunnels drilled half a kilometer into living rock, pressurized, climate-controlled, stocked for years of autonomous operation. Engineers call it hardened infrastructure. The Iranian military calls it a missile city. The question isn't whether it exists. Satellite imagery already confirmed that. The real question is this: how do you build something that even a direct nuclear strike cannot reach? And how exactly does the mountain breathe? Every surface installation Iran ever built got photographed. From 400 kilometers above the Earth, American KH-11 reconnaissance satellites resolve objects 15 centimeters across. 15 centimeters, the width of a coffee mug. Nothing on the surface of Iran was secret. Launch pads at Shahrud, photographed. Missile assembly facilities at Parshan, photographed. Fuel depots, radar arrays, command posts. All of it visible, all of it targetable. The engineers understood the problem clearly. Anything they built above ground was already dead. Iran sits inside a geography that looks, from the outside, like pure vulnerability. 1,600 kilometers of Gulf coastline exposed to the Fifth Fleet. Airspace dominated by American bases in Qatar, Bahrain, the UAE. Israeli F-35s with a combat radius that reaches Tehran without refueling. Every strategic asset sitting in the open desert, under permanent surveillance, inside someone else's targeting computer. One strike package, one night. Everything gone. So the engineers looked at what Iran actually had. Not allies, not air superiority, not advanced surface-to-air coverage across every grid square. They had the Zagros. The Zagros Mountains run 1,500 kilometers from northwestern Iran down through the spine of the country. Ancient folded rock, Jurassic limestone and dolomite compressed over 150 million years into formations that reach 4,000 meters above sea level. The rock is dense, competent. In geological terms, that means it holds load. It doesn't fracture randomly. It doesn't collapse under pressure without warning. It is, structurally, almost ideal for what the engineers had in mind. The hardest conventional bunker-busting munition in the American arsenal, the GBU-57 massive ordnance penetrator, punches through 60 meters of reinforced concrete before detonating. 60 meters, the tunnels go down 500. The mountain didn't need defending. It simply needed to be opened up and turned into the weapon itself. The first instinct is always concrete. Pour enough of it, reinforce it deep enough, and you have a bunker. The Soviet Union built bunkers under Moscow, multi-layered, blast-hardened, connected by subway tunnels. The Americans built Cheyenne Mountain into a Colorado granite peak, suspended the entire command center on 1,300 steel springs to absorb nuclear overpressure. Bunkers work until they don't. The problem with a bunker is geometry. It sits in one place, its coordinates are fixed. Given enough penetrating munitions, enough passes, enough patience, a fixed point can always be reached. The Iranian engineers chose a different logic entirely. Not a point, a network. Tunnels don't have a single address. A tunnel system 500 meters deep with dozens of branching corridors. Multiple access portals spread across kilometers of mountain face. That is not a target. That is a geology problem. And geology problems don't get solved with strike packages. The decision came down to rock mechanics. At 500 meters depth in competent Zagros limestone, the overburden pressure itself becomes structural. The rock above isn't just sitting there passively, it's compressed, interlocked. The tunnel, bored correctly, redistributes load around the void in an arch. The same principle a Roman aqueduct uses, transferred into living stone. The mountain becomes self-supporting. No concrete lining required in the hardest sections. The geology does the work. For excavation, they used drill and blast, not tunnel boring machines. TBMs are faster, cleaner, more precise. They are also 150-ton pieces of German or Chinese engineering that break down, require proprietary parts, and cannot navigate the fractured fault zones that run through Zagros limestone unpredictably. Drill and blast is slower. It is brutal. It is also repairable with tools that exist inside a sanctioned country. The engineers chose what they could fix, because a tunnel that stops halfway through a mountain is just an expensive cave. The first problem underground is heat. Rock at 500 meters depth holds an ambient temperature of around 30 to 35 degrees Celsius. That's before you add the exhaust from diesel drilling equipment, the friction heat of blast operations, the body heat of hundreds of workers operating in a sealed environment. The tunnel breathes badly at first. It barely breathes at all. Early excavation crews work in wet heat that soaks through clothing in minutes. Core temperature rises. Reaction time slows. A worker operating a jackleg drill in 38-degree tunnel air makes mistakes. Mistakes at the face of a blast hole, where someone has just packed explosive, are not recoverable. Ventilation comes first, before depth, before speed. The engineers drive auxiliary ventilation shafts, narrow vertical bores, sometimes only 60 centimeters in diameter, down from the mountain surface to the active tunnel face. Massive centrifugal fans, some pulling 300 cubic meters of air per minute, force fresh air down through flexible ducting that extends as the tunnel advances. The duct grows with the excavation. A kilometer of tunnel needs a kilometer of duct, suspended from the crown, patched where it tears, replaced where the blast overpressure collapses it. The duct tears constantly. Groundwater is the second enemy. Zagros limestone is karst, meaning water has been dissolving it from the inside for millions of years. Hidden voids. Fracture networks saturated with ancient water under pressure. The drill bit punches through a competent rock face, and suddenly the tunnel face weeps, then runs, then floods. Pumping systems work around the clock. Iranian-manufactured submersible pumps, because no Grundfos service engineer is flying into a classified military excavation site under sanctions. When the pumps fail, workers bail by hand. And through all of this, the heat, the water, the torn ducting, the broken equipment, the excavation advances. Slowly, 3 to 4 meters per day in good rock. Less in bad, the mountain resists, the crews keep cutting. Now the numbers, made physical. 500 meters of rock overhead, not 500 meters of air, 500 meters of compressed Zagros limestone, averaging 2,700 kilograms per cubic meter. That column of stone above a single tunnel section weighs more than the entire displacement of a Nimitz-class aircraft carrier, per linear meter. The mountain doesn't notice the tunnel beneath it. That is the point. The tunnel diameter, between 8 and 14 meters in the main corridors. Wide enough for a Shahab-3 transporter erector launcher, a vehicle 14 meters long, 3 meters wide, carrying a missile that weighs 16 tons fully fueled. These machines don't turn easily. Every corner radius in the tunnel network was engineered around the turning circle of the launcher. The tunnel exists to serve the vehicle. The vehicle exists to serve the missile. The rail system runs the length of the main corridors. Steel track embedded in reinforced concrete floor. Gauge matched to launcher wheel spacing. The launcher rolls. It doesn't drive, it rides. Precise, controlled, silent, except for the steel-on-steel contact that echoes off tunnel walls. Back to a crew that has rehearsed this movement hundreds of times in darkness. Blast doors. Each one between 8 and 12 tons of hardened steel mounted on hydraulic hinges, designed to seal a tunnel section against a pressure wave of 50 kilopascals. That is the overpressure generated by a near miss from a GBU-57 at the surface detonation. The doors don't just close, they breathe shut, hydraulic seals compressing around the frame, making the section behind them a separate pressure vessel. Power. Independent diesel generation. Fuel storage calculated for 18 months of autonomous operation. Air filtration rated for NBC. Nuclear, biological, chemical contamination. Water, food, medical. Communications routed through fiber, not radio, because radio signals leak through rock. And tell people where you are. The city under the mountain doesn't need the surface. That is precisely the design requirement. The doors open at 300, not because dawn offers cover, because the thermal differential between night air and tunnel air is smallest at 0300, meaning the infrared signature of the opening is at its minimum. The rush of pressurized tunnel atmosphere meets cold mountain air. The engineers calculated this. They calculated everything. The launcher rolls out on its rails, 18 seconds from door open to launch position. The crew doesn't run. Running suggests panic. This movement is choreographed, practiced until it lives in muscle memory, not conscious thought. The erector arm rises. The missile reaches vertical. The mountain stands behind it, unchanged, indifferent, giving nothing away. What has actually been built here is not a weapon system. It is a problem without a solution. Every military doctrine built around deterrence assumes the other side has something to lose on the surface. A launch facility, a command structure, a power grid, infrastructure that bleeds when you strike it. The missile city has none of that exposure. Strike the mountain and the mountain absorbs it. The tunnel network redistributes the shockwave through kilometers of branching corridors, dissipating energy the way a river delta dissipates floodwater, into 1,000 smaller channels until it becomes nothing. The engineers who built this didn't solve a military problem. They solved a physics problem. Overpressure, thermal signature, structural load distribution, ventilation fluid dynamics. The weapons came later. The engineering came first, and that is what makes it permanent. Doctrine changes, alliances shift, governments fall, but 500 meters of competent limestone doesn't renegotiate. The mountain doesn't change its position based on the political climate. It simply sits there, holding its load, keeping its secret, which leaves one question the engineers cannot answer. Not whether the system survives a strike, whether any system this hardened, this patient, this invisible, ever gets used at all, or whether the most sophisticated deterrent ever built underground simply waits forever. For a moment, that never comes.